Welcome to Combinatorics class. We are now starting to learn about graph theory, and we're following the textbook Combinatorics and Graph Theory. So one of the reasons why we're interested in graphs is that they can be used to model many situations. And one of the most famous problems is called the four-color map conjecture. The conjecture states that the maximum number of colors required to color any map where bordering regions are colored differently is 4. So I'll be talking about section 111. So you can think of a graph using this visual representation. So a graph consists of two finite sets, V, which is the set of vertices. So in this example, the vertices are A, B, C, D, E, F, G, H, which are represented by these dots. And then we also have a set of edges. So the edges are unordered pairs of vertices. In this case, we have these edges for our graph. So together, the two sets, V and E, are the graph G. But normally, when we talk about a graph in this class, we will think of this visual representation. Instead of having a set of unordered pairs of vertices, we can consider a set of ordered pairs of vertices. So this would be called, so if we have vertices plus these ordered edges, or we get what's called a directed graph or digraph. In this example, the vertices are A, B, C, D, and E, and we have 7 edges. So we have the edge from E to A to B. We also have B to D, and then D to C, and C to D are different from the edge from D to C. We can also consider a situation where we allow repeated elements in our set of edges. So we replace our set with a multi-set. So this is called a multigraph, but in other places, often this is just called a graph. And here are more other generalizations of a graph if you're interested. So pseudograph and hypergraph. But in this chapter, we will focus on graphs with finitely many vertices and simple graphs, which means that they do not have loops and they do not have multiple edges. So let's look at this problem. So we want to model this situation using a graph. We have 6 people that are seated around a circular table, and each person shakes hands with everyone at the table except the person sitting directly across the table. And we want to draw a graph that models this situation. So let the 6 people be labeled by 1, 2, 3, 4, 5, 6. So for example, the person 1 would shake hands with everyone except for the person 4, because 4 is sitting across from 1. So 1 shakes hands with 2, 3, 5, and 6, and so on. And it makes sense for this situation to be modeled by a graph, because when you're shaking hands, it's like you're both shaking hands with each other. So it makes sense that your edges are not ordered. In the second situation, we want to pair off as roommates a group of people, and each person has compiled a list of the people with whom they would be willing to share a room. So there are 6 people. So let them be A, B, C, D, E, F. And so for example, Adam says that he's willing to room with Doc. So then A is pointing to D. And then Bert is willing to share a room with 2 people, Adam and Ernie. So then B would have an edge pointing to A and also an edge pointing to E. So in this situation, it makes sense to have a digraph modeling the situation.